Welcome to this course, Global Warming, How Does It Work? Why does carbon dioxide in the atmosphere heat, not cool the Earth? How is the atmosphere opaque for some infrared wavelengths? Would reducing emissions now have much effect on Earth's temperature? Let's see what we can calculate without being climate scientists. This is a course I created in 2024. It started with these 3 questions, but expanded beyond them, as we shall see. Here's the roadmap or table of contents. I'm going to read this out, but you can skip that if you don't want to hear it. Introduction 1, questions, abstract. Introduction 2, carbon dioxide absorption bands, absorption cross-sections for carbon dioxide, spectral density, net effect, false arguments, methane, sulfur dioxide, water vapor, carbon dioxide absorption at the bottom of the atmosphere, absorption versus altitude, carbon dioxide absorption at the top of the atmosphere. 100% absorption. Why would additional emissions be bad? Earth's energy imbalance, absorbed and re-radiated power, global warming, radiative forcing, climate sensitivity and feedbacks, MODTRAN immediate radiative forcing, MODTRAN projection for 2050. Massive carbon dioxide in the atmosphere, concentration, emissions and goals, integrated assessment model, past temperatures higher than now, sea level rise, past concentrations higher than now, oceans and carbon dioxide, climate change uncertainty, skepticism, and denial, climate denial article and exercise. Is methane absorption stronger than carbon dioxide? Methane concentration, emissions, and goals. Methane emission sources. Reducing methane. Methane uncertainty, skepticism, and denial. Section 1, Introduction 1. We will learn about the underlying basis for climate change and global warming, the greenhouse effect of increased heating of the Earth's surface by the presence in the atmosphere of the greenhouse gases, water vapor, carbon dioxide, and methane. A very smart engineer friend, climate skeptic or perhaps denier, asked me some good questions about carbon dioxide in the atmosphere. I thought I knew the standard answers, but was not certain. So I found some basic data on the internet and did some calculations. We will use some physics, some math, and 2 modeling tools. You don't need to follow the physics and math in detail. I'm sorry if some parts might get tedious. I hope you will get oriented, will learn some of the physical processes, ideas, and terms, and we'll see which results are consistent with simple calculations, which you could try for yourself. Articles should then be a little more accessible. I'm an engineer, not a climate scientist or a scientist at all. We cannot prove that climate scientists are correct, though our results will generally support their position and explanations. We will see some issues that are complicated, require complex physics and climate modeling, and are more difficult for us laymen to accept on faith or identify the assumptions or uncertainties for ourselves. Late in the course, we will discuss some climate skeptic positions. This lecture script is available as a PDF. The link is in the description of the video. Attributions for the images are given in the lecture script PDF. Section 2, Questions. Why does absorption by carbon dioxide in the atmosphere heat the Earth, not cool it? How plausible are the following? 100% atmospheric absorption at carbon dioxide wavelengths. Absorption and re-radiation of 1 watt per square meter of power. Raising Earth's temperature by 1 degree Celsius. Reducing emissions is very difficult, costly, and political. A good question is, how much heating could be averted by reducing emissions? We won't be able to quantify this last question, but we will come to see why it is a difficult issue. Mainstream climate scientists agree on a range of probable outcomes, but not a tight value. Section 3, Abstract. I did calculations that say that carbon dioxide's 15 micron wavelength band contributes strongly to greenhouse effect heating. The 2 and 2.7 micron wavelength bands contribute to cooling, but are weak. The 4.3 micron wavelength band absorbs strongly but contributes nearly equally to heating and cooling. We will see this. The total effect of carbon dioxide summed over all wavelengths calculated to net heating. However, we will see late in the course how the impact of continuing to add carbon dioxide to the atmosphere is too complicated for simplistic analysis and is central to skepticism or denial of human-caused climate change. Section 4, Introduction 2. Gases in the atmosphere that absorb and re-radiate infrared photons would do so for radiation from the sun, as well as thermal radiation from the Earth. Why should this cause heating and not cooling? A good question. I thought that it would be relatively straightforward to show that carbon dioxide has much greater greenhouse effect heating the Earth than cooling it by re-radiating infrared from the sun. I did simplified calculations which confirmed greenhouse heating as climate scientists say, but it's complicated and my assumptions were necessarily simplistic. I am trusting data, charts, and information from Google search and websites, sometimes not checking for authoritativeness. Molecules, dust, aerosols, and clouds in the atmosphere absorb electromagnetic radiation at specific wavelengths, ranges, or bands, as we will see, whether the radiation comes from the sun, the surface of the Earth, or was emitted by the atmosphere. The atmosphere is transparent mostly at some infrared wavelength bands and opaque at others. This diagram shows several cases. For wavelengths for which the atmosphere is transparent, the photon will pass through the atmosphere, either from the sun to the Earth's surface, shown here, or from Earth's surface to outer space, here, or if the photon was emitted from a molecule in the atmosphere, it will either escape to the Earth's surface or to outer space. These are the blue arrows. The brown examples are wavelengths which will be absorbed by the atmosphere. Photons emitted by the sun will be absorbed in the atmosphere and not reach Earth's surface directly. Photons emitted from the surface of the Earth will be absorbed in the atmosphere and not reach outer space directly. Photons emitted by molecules in the atmosphere at specific emission wavelengths will generally be absorbed in the atmosphere, often by the same molecule type. Unless the emitting molecule was close to the surface of the Earth or close to the top of the atmosphere. The thick atmosphere is opaque for these wavelengths, but it is a little complicated. If the original absorbed photon was from the sun, the effect of the absorption and remission, which I will call re-radiation, is to reduce the amount of radiation reaching the surface of the Earth, a reduction of heating, so a cooling effect. If the original absorbed photon was from the surface of the Earth, the effect of the absorption and re-radiation will be to reduce the amount of radiation reaching the top of the atmosphere and escaping to outer space. An increased heating of the atmosphere and Earth's surface, called the greenhouse effect. When a molecule in the atmosphere absorbs a photon of some specific wavelength, some sources wrongly say that the excited molecule then re-emits a photon at the original wavelength in a random direction, re-radiates isotropically. This is wrong and misleading. Better sources say that the molecule shortly collides with other molecules. The added energy thermalizes among the molecules, very slightly raising the local temperature in the atmosphere, and eventually a thermal photon at some emission wavelength is emitted or re-emitted in a random direction. Sometime after the original photons are absorbed, the atmosphere returns some energy toward the original source, which would not occur if there were no absorption and the atmosphere were completely transparent. If you want more information about how absorption at one wavelength leads to emission at another wavelength, for which the atmosphere is nearly transparent, see my 20-minute video here. Neglecting clouds. For the infrared range corresponding to thermal emission from the Earth's surface, or from molecules in the atmosphere, there are wavelength ranges with 100% absorption or scattering by the atmosphere, opaque blanket ranges, blanket wavelengths, and other wavelength ranges that are fairly transparent, called window wavelength ranges or windows. In this course, when I say 100%, take it to mean greater than 99% or 98%. Clouds reflect some sunlight back to space, part of Earth's albedo or reflectivity. If there were albedo and emissivity but no greenhouse effect, Earth would be something like 66 degrees Fahrenheit, 37 degrees Celsius, cooler than it is, and pretty well frozen over. So, we depend on greenhouse gases in the atmosphere for most life on Earth. Planet Venus would be cooler by 870 degrees Fahrenheit, 480 degrees Celsius, if it had no atmosphere with greenhouse effect. Most of the greenhouse effect on Earth today, and perhaps throughout Earth's history, is due to water vapor, which long ago raised the temperature on Earth beneficially to life. The second largest greenhouse effect today is due to carbon dioxide. The greenhouse effect from additional carbon dioxide and methane that we humans have emitted in the last 150 years, though small relative to the total effect of water vapor, is said to have produced an energy imbalance of about 1 extra watt per square meter radiated from the atmosphere to the surface. This is said to be the cause of recent warming of the Earth, melting glaciers, thawing Arctic permafrost, and thinning Arctic ice pack. We have not yet reached steady state for the emissions of the past 100 years, and we continue to emit. But that's jumping ahead. Section 5. Carbon dioxide absorption bands. I am trusting this diagram throughout this course. The horizontal axis is electromagnetic radiation wavelength in microns, millionths of a meter, on a logarithmic scale, going from short wavelength ultraviolet on the left and visible light to long wavelength infrared on the right. Beware, some graphs you may see on the internet use wave number in inverse centimeters and are flipped left to right. The red curve is the ideal blackbody thermal radiation spectrum for the sun's temperature. Radiated energy intensity per unit wavelength per unit area at Earth's orbital distance from the sun. The wavelength peak here is in the visible range. Actual radiation from the sun differs a little from ideal blackbody. The orange area here is sunlight intensity directly reaching Earth's surface, having not been scattered by or absorbed by atmospheric gas molecules, dust, aerosols, water droplets, or clouds. The orange area is beneath the red curve. But Earth's surface also receives some radiation scattered by or emitted by the atmosphere. So radiation intensity reaching Earth's surface, combining direct and indirect, is a different curve not shown here. The atmosphere causes some radiation from the sun to be scattered or re-radiated back to outer space. So the Earth's surface would seem initially to be cooler than if we had no atmosphere or the atmosphere was transparent. But we also need to include the greenhouse effect. The magenta, blue, and green curves are ideal blackbody thermal radiation spectra for idealized thermal emission from Earth's surface at different temperatures. These are in the infrared range. These curves assume Earth's surface is a nearly perfect blackbody in the infrared range. The magenta curve is for 37 degrees Celsius, 100 Fahrenheit. The green curve is for minus 63 Celsius, minus 82 Fahrenheit. For higher temperature, the peak moves to shorter wavelength, to the left, per Wien's displacement law. The peak intensity also increases sharply with temperature to the fifth power, but these are graphed here normalized to their respective peak intensities. So beware, we cannot directly compare these intensities to the sunlight intensity using this graph alone. Think of the red curve as about 80 times taller than the blue curve, depending on the temperature of the blue curve. The widths at half maximum for the four solid curves, so the width, decrease as temperature increases, but the logarithmic scale makes them look the same unless we really think about it. The blue area here is thermal emission from Earth's surface that directly reaches outer space and escapes, having not been scattered by or absorbed by gas molecules, dust, aerosols, water droplets, or clouds in the atmosphere. The blue area is beneath the blue curve. The blue area is 0 for some wavelength bands, such as 5.5 to 7.5 microns and 20 microns to 70 microns. 100% absorption by the atmosphere of radiation from Earth's surface in those bands. But the atmosphere scatters and emits radiation in all directions. Some of this radiation reaches Earth's surface and some reaches outer space and escapes. So radiation intensity reaching outer space, combining direct and indirect, is some curve mostly between the blue area and the colored curves. Energy intensity escaping to outer space will not go down to 0 where the blue area is 0. So, this image notwithstanding, outer space does receive some radiation at 6 microns, 7 microns, 15 microns, 30 microns, 40 microns, etc., from emission by some altitudes of the atmosphere, not directly from Earth's surface. Later, we will look at curves of radiation intensity reaching outer space. At wavelengths for which the atmosphere is pretty transparent, like here, radiation will reach outer space emitted from Earth's surface and also emitted from the atmosphere. At wavelengths for which the atmosphere is 100% absorbing, like here, radiation will reach outer space emitted only from the atmosphere, which is generally colder than Earth's surface. We will look at this later. The atmosphere causes some infrared thermal radiation from Earth's surface to be scattered or re-radiated back to Earth's surface. So the Earth's surface gets warmed by this greenhouse effect. But actually, climate scientists focus on how much radiation escapes or does not escape from the top of the atmosphere to outer space. Their perspective is that continuing to emit great amounts of greenhouse gases reduces the amount of Earth's thermal radiation that escapes from the top of the atmosphere to outer space. And that reduction drives or forces increased temperature of Earth's surface and the atmosphere. So, the atmosphere has both a cooling and heating effect. It's complicated. The gray area, here, there, is the absorption and scattering by the atmosphere between Earth's surface and outer space in either direction. Multiple wavelength ranges have 100% absorption or scattering between bottom and top of the atmosphere. It's 100% here, there. Where infrared absorption is high, the blue area is well below the blue curve, going down to 0. So the gray curve is 100% here, and the blue area is 0. Same for here and here. Note that the peak of the blue curve is within the transparency window of the gray area. Next, we will see the causes of the absorption. The cyan, or light blue area, is absorption and scattering by water vapor, the strongest greenhouse gas with the most impact on Earth's temperature. When some article calls carbon dioxide the strongest greenhouse gas, it is because they are excluding water vapor and focusing on human-caused anthropogenic emissions. Notice that the infrared cuts in the sunlight orange area are due to absorption by water vapor, a partial cooling effect. So this cut is due to water vapor. This cut is due to water vapor, and so on. Notice the pink box. This is the water vapor window from 7.5 microns to 20 microns, where water molecules in the atmosphere only partially absorb radiation from the Earth's surface. Notice that the peak of thermal emission from the surface of the Earth is within this water vapor window for a wide range of surface temperatures. So a good amount of thermal radiation escapes to outer space if water vapor were the only greenhouse gas. Notice that there is some amount of absorption or scattering at almost all wavelengths in the water vapor window. It is not completely transparent. This is important. Water molecules in the atmosphere can emit radiation in this window, and it will escape the atmosphere. The brown or mustard area is the absorption by carbon dioxide. One of the absorption bands, this one, is within the water vapor window, the pink box. There are 4 significant bands here. This one, 2, 3, 4. Let's switch to this next diagram, which puts water vapor and carbon dioxide on the same graph. Blue-gray areas are for water vapor. Brownish areas are for carbon dioxide. I assume this graph corresponds to carbon dioxide concentrations of recent decades, but I wasn't able to get that information. Notice the water vapor window here, 7.5 to 20 microns. Let's call the partial transmission wavelength window between 7.5 and 14 microns, the green box, the water vapor carbon dioxide window, for the purpose of this course only. It's not a standard term. This carbon dioxide band is nearly 100% absorbing down to the edge of the green box, 14 microns. So the green box is only partially absorbing, mostly transparent. We will assess the 4 carbon dioxide absorption bands centered near 2 microns, 2.7 microns, 4.3 microns, and 15 microns. These are my names for the bands. Others may call them 4.23, 4.27, 14.9. Notice that the 2.7 micron band coincides with 100% absorption by water vapor, so it has less impact, but the other bands do not. The 15 micron band is broad and within the water vapor window. where thermal emission from the Earth's surface is high. This band absorbs some of that radiation and is responsible for carbon dioxide's greenhouse effect, as we will see. Since there is radiation from the sun and from Earth's surface, atmospheric absorption and isotropic re-radiation has both a warming and cooling effect, but not equally. Using the width of the absorption bands and the spectral intensity of sunlight and Earth's thermal radiation, we will calculate that the 15 micron band absorbs more of Earth's thermal radiation than of sunlight, raising Earth's temperature. And the 2.7 and 2 micron bands do the opposite, lowering Earth's temperature. But I want to relate this to carbon dioxide molecules in the next section. We will calculate that wavelengths shorter than about 4.2 microns, so to the left of my cursor, are net cooling for Earth, and wavelengths longer than 4.2 microns, to the right of my cursor, are net heating. Further from that crossover is greater imbalance. We will identify which absorption bands I think are net cooling versus net heating. Later, we will estimate the amount of power returned to the Earth. Section 6, Absorption Cross-Sections for Carbon Dioxide. The absorption of infrared radiation at a point in the atmosphere is a function of molecules, aerosols, dust, and clouds. For a given molecule, different absorption wavelengths have different strengths, differing by many orders of magnitude. Here's a graph of carbon dioxide's infrared absorption cross-sections in centimeters squared per molecule versus wavelength in microns. This is the cross-sectional area over which a given molecule is likely to absorb an incident photon of that wavelength. Larger value means higher probability for absorption, and also higher probability for emission. Infrared absorption is due to quantum mechanical, quantized, rotational, vibrational resonance modes, rho vibrational, and is complicated. Each vibrational mode is accompanied by a large number of rotational transitions. I'll call each spiky forest a band for ease of wording. This is not the same as an electronic band in semiconductors. These graphs are a composite of 3 temperatures, 5, 25, and 50 Celsius, and 10 partial pressures of carbon dioxide backfilled with nitrogen to 1 atmosphere. So they represent some kind of average of the bottom of the atmosphere, not the top, which would look very different, and they represent some range of concentrations of carbon dioxide, not a single concentration. For molecules, absorption is a function of wavelength, composition, like is it carbon dioxide or is it methane, concentration, pressure, and temperature. Climate modeling must use data for the relevant pressures and temperatures at different latitudes and altitudes, but we will use this graph as representing an average. There are 7 graphs. They have different scales, 2 different scales. This first graph has a scale 10 to the minus 18, and some of the graphs zoom in by a factor of 1,000. So the vertical scales are 10 to the minus 18, 21, 21, 18, 21, 21, and 18 centimeters squared per molecule. The first graph shows 2 to 18 micron wavelengths on one graph. The 4.3 micron band looks strongest. Then the 15 micron band, though it also has a wide band of lower cross-section that we don't see in the 4.3 micron band. And this wide band is very important to global warming. The 2.7 micron band is weak, and we cannot see the 2 micron band at all on this graph. The other graphs show detail for each band. Here is the 2 micron band, the weakest band. We see the spiky forest. Here is the 2.7 micron band. The scale is 10 to the minus 21, but here it goes up to 200 versus 5, so the 2.7 micron band is more absorbing than the 2 micron band. Here is the 4.3 micron band. There are peaks, and then there are skirts and valleys, but it looks like the valley does not go to 0 absorption at the bottom of the valley. We will skip the next 2 graphs, which are low absorption wings of the 4.3 micron band. The final graph is the 15 micron band, with the same scale as the 4.3 micron band. The 15 micron band is due to the bending or flexing of the carbon dioxide molecules, not linear vibration, and then rotation of the flexing molecule along one or more axes. Carbon dioxide is a linear molecule, but it can bend. The peak of the 15 micron band looks different than the 4.3 micron band looked. It's tall and broad. We will see much later that this actually consists of many individual absorption wavelengths. I will approximate those graphs as the following absorption bands and strengths. The number after the colon is my estimated area under the absorption cross-section curve for that band, the width of the band times the average absorption cross-section for the band, in units of micron centimeter squared per molecule, divided by that value for 4.3 microns, so that the 4.3 micron final value will be 1. So the value for 2.7 is about 100 times smaller. The value for 2 microns is about 100 times smaller than that. And the value for 15 microns is about comparable to the value for 4.3 microns. I don't know the value exactly, so I estimated it as from 0.6 to 1.1 times the 4.3 micron value. Later, I improved these estimates by summing the high-tran spectral line intensities. Contact me if you want to know more. So these values are proxy estimates for the relative amount of absorption if the same radiation spectral density were present at each band, which will not be the case. The 4.3 micron band seems comparable to the 15 micron band, and the other two bands have much weaker absorption. Section 7, Spectral Density. Now we calculate the blackbody radiation spectral energy density per unit wavelength, present for each carbon dioxide wavelength for sunlight entering the top of the atmosphere and thermal radiation from Earth's surface into the bottom of the atmosphere. I used the sun photosphere temperature of 5,772 Kelvin, which would have a wavelength spectrum peak at half a micron, here, in the visible range. However, some graphs use other temperatures such as 5250, 5500, 5525, trying to fit to data. This difference doesn't matter much and doesn't matter at all for this course. The Earth's global average surface temperature, averaged over a few years, is about plus 15 degrees Celsius, which would have a spectrum peak at 10 microns in the infrared. Of course, the temperature of Earth's surface is not uniform or constant, nor is temperature within the atmosphere, so this may be too simplistic. Let's see what we get. I used Planck's blackbody spectral energy density formula. The results are in joules per meter to the fourth. Alternatively, I could have used the formula for spectral radiance. This would have a constant multiplicative factor in different units, watts per cubic meters to radian, but no change to the argument. At each carbon dioxide absorption wavelength lambda, and for the temperature T of the sun or the Earth average, I calculated the spectral energy density. Then I divided the solar value by the square of the Earth's distance from the sun divided by the sun's radius to get the solar value at the top of Earth's atmosphere, at a point directly in line between Earth and sun, where the sun is directly overhead. Then I divided that solar value by 4 to get the average across the sphere of the Earth, day and night sides. And here are my calculations. So the graph and the table correspond. There are values for 2 microns, which is here, 2.7 microns, which is here, 4.3 microns, which is here, and 15 microns, which is here. The first value after the colon is for sunlight at the top of the atmosphere, averaged across the Earth, including the night side. So, this value. These are the blue dots on the graph. These values decrease with longer wavelength, further from the sun's peak wavelength of half a micron. So, decrease, 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 decrease. 3 times 10 to the minus 1, 1 times 10 to the minus 1, 2.4 by 10 to the minus 2, 2 times 10 to the minus 4. The second value after the colon is for thermal radiation from the Earth's surface at plus 15 Celsius into the lower atmosphere with a peak wavelength at 10 microns. That's the red curve, and we see that the peak is at 10 microns. So these are the red dots on this graph. The 4.3 micron value is about 8 times smaller than the 15 micron value. 15 micron value is 2.4 by 10 to the minus 1, and the 4.3 value is 2.9 by 10 to the minus 2. The 2.7 and 2 micron values are much smaller. The third value is the Earth value minus the Sun value. Positive if absorption will cause net heating. Negative if absorption will cause net cooling. The crossover for this calculation is about 4.2 microns at plus 15 Celsius, but it's a function of temperature. The 2 and 2.7 micron bands, they would absorb and re-radiate much more infrared radiation incoming from the sun than outgoing from the Earth's surface. So they contribute to cooling the Earth. The sun value is much larger than the Earth value. The sun value is much larger than the Earth value. The third number is negative, and the blue dot is higher than the red dot. The 2.7 micron band is already opaque from water vapor, but carbon dioxide has much higher concentration than water vapor at the top of the atmosphere, so carbon dioxide is doing this absorption high in the atmosphere, but water vapor would do it lower in the atmosphere, even if the carbon dioxide were not present. The 15 micron band would absorb and re-radiate 1,000 times more infrared outgoing from the Earth's surface than incoming from the sun. This value is nearly 1,000 times this value. So, the 15 micron band contributes to heating the Earth, the greenhouse effect. The red dot is higher than the blue dot. In fact, it's 1,000 times more higher value. The 4.3 micron band has mixed effect, absorbing and re-radiating only slightly more from the total Earth at constant plus 15 Celsius than from sunlight averaged over the Earth. So using an average temperature for Earth's surface is too simplistic. The crossover temperature for the 4.3 micron band calculated to plus 10 Celsius, so slight cooling dominates at colder temperatures for that band. So whether the 4.3 micron band is slightly net heating or slightly net cooling over a day depends on location on Earth, especially latitude, and altitude in the atmosphere. Section 8, Net Effect. Now we multiply the third number from that table, Earth minus Sun, with the number from the earlier cross-section table. Other than the sign, this is a sort of proxy for absorbed power per molecule. We will assume this is a reasonable proxy for thermalized and re-radiated power per molecule, which we will assume is a reasonable proxy for additional power radiated by the atmosphere in transparent windows. This is good enough for this section's plausibility check. So for 2 microns, I got minus 4 by 10 to the minus 5, which is very slight cooling. For 2.7 microns, I got minus 1 by 10 to the minus 3, slight cooling. For 4.3 microns, I got plus 5 by 10 to the minus 3, slight heating, slight net heating, but the value would depend on the average temperature we use for the Earth. And for 15 microns, I got 0.16 to 0.27, much higher than any of these other numbers, significant heating. So, according to these measures, the 15 micron wavelength band causes 6 to 10 times more greenhouse heating than the solar cooling effect from the other bands. This is because it is close, a factor of 1.5, to the 10 micron peak for Earth's surface thermal radiation and has a high absorption cross-section. The 4.3 micron band has a high absorption cross-section, but is near the crossover wavelength between sunlight and the Earth's thermal radiation, so it cools and heats comparably averaged over the Earth. My calculation was that the 4.3 micron band net heats at 15 Celsius average surface temperature, but net cools below 10 Celsius. A better analysis should take into account temperatures across the Earth and the atmosphere temperature profile. The total effect of carbon dioxide summed over all wavelengths calculated to net heating when the average surface temperature of the Earth was above minus 100 Celsius, consistent with climate scientists' explanations. The average surface temperature of the Earth has never been that cold. So, it is plausible that absorption by carbon dioxide in the atmosphere net heats the Earth, not cools it. That was the first question we asked in this course. Later, we will see the effect of continuing to add more carbon dioxide to the atmosphere. Venus has a carbon dioxide atmosphere and is much hotter than the Earth, and not because it is closer to the Sun. On Venus, the crossover wavelength calculates to about 1.6 microns at present temperature. So all 4 carbon dioxide absorption bands are net heating and more strongly than on Earth. Venus had runaway greenhouse effect billions of years ago that heated it to its current temperature. Hot enough to melt lead, hotter than the maximum temperature on Mercury, which has only a trace atmosphere. If Venus ever had water vapor, it is now long gone. It would have evaporated and then escaped to outer space. A water molecule has lower molecular weight than a carbon dioxide molecule. Water molecules reached escape velocity, but carbon dioxide did not. Section 9. False arguments. Here is one false argument. The Sun's temperature is higher than the Earth's temperature, so the spectral density at any wavelength will be higher for the Sun's temperature than for the Earth's temperature. That is true for the surface of the Sun and the surface of the Earth. But for sunlight spectral density at Earth's orbit, we have to reduce the Sun's spectral density by the square of the appropriate distance ratio. So it is not true. Here is a second false argument. The solar irradiance at Earth's distance from the Sun is higher than the radiation watts per square meter radiated from the Earth, so maybe the re-radiation of radiation from the Sun should always be higher than re-radiation of radiation from the Earth. No. Radiation from the Sun intercepts the Earth's disk area, pi r squared. Radiation from the Earth emits from the sphere surface area 4 pi r squared, day and night, pole to pole. Taking the factor of 4 into account, and albedo and emissivity, Earth's surface radiates something like 65% more power into the lower atmosphere than the surface and atmosphere absorbed from the Sun after reflection from clouds. Some of the excess gets returned to the surface and some gets radiated into space. Section 10. Methane. Methane, CH4, has an absorption band at 7.6 microns, which is greenhouse warming and close to the thermal peak around 10 microns. Half of this band overlaps with 100% absorption by water vapor, which reduces methane's impact. The methane band is not 100% absorbing, whereas the carbon dioxide 15 micron band is 100% absorbing and wide. So the present concentration of carbon dioxide has more absorption and has produced higher greenhouse gas global warming than the present concentration of methane, but the incremental impact of methane is higher. Websites say that methane in the atmosphere is a much stronger absorber of Earth's thermal infrared radiation than carbon dioxide. They may not say so, but I believe this is for new emissions adding to the present concentrations of about 1.9 part per million methane and 420 parts per million of carbon dioxide. 200 times more carbon dioxide. We will look at this further in a separate video on methane toward the end of the course. Section 11. Sulfur dioxide. Sulfur dioxide has an absorption band near 7.5 microns, but is not listed as a greenhouse gas. This is because it forms sulfuric acid within 2 weeks, and then progresses to sulfate aerosols that scatter and absorb in the visible spectrum, sunlight, and cool the Earth. Aerosols in the atmosphere are condensation nuclei that allow water vapor to form smaller water droplets than would form in the absence of aerosols. This has a cooling effect, but with large uncertainty. Cooling by aerosols has slightly to somewhat offset the heating due to carbon dioxide and methane. But aerosols and water vapor can change the amount of cloud cover and change Earth's albedo. Sulfur dioxide, ash, and smoke from a major volcanic eruption can cool the Earth for a few years, and smoke from wildfires can cool the Earth slightly for a shorter period. Heating the oceans may release some amount of sulfur dioxide, but I think the effect is smaller than for carbon dioxide released from warm ocean regions. More about aerosols later in the course. Section 12. Water vapor. Clouds. Opaque white or gray clouds in the lower troposphere, here. For example, cumulus and stratus clouds scatter and diffusely reflect sunlight back to space and account for the atmosphere's albedo and most of the Earth's albedo, cooling the Earth. Wispy, transparent cirrus clouds, here, at the top of the troposphere, heat the Earth by absorbing and re-radiating the Earth's thermal infrared radiation. How global warming affects clouds is the biggest uncertainty for climate modeling and climate sensitivity. One difficulty is that cloud size is smaller than the grid size for global climate modeling. We will ignore clouds in this course, but remember that they are a large uncertainty in modeling and prediction. Water vapor is a very strong greenhouse gas. There are something like 10 times as many water vapor molecules in the atmosphere than carbon dioxide molecules. I don't know if this includes clouds. Water vapor has absorption bands throughout the infrared spectrum, as we see for the cyan area in this graph. Water vapor and clouds strongly scatter and re-radiate light from the sun and infrared from the Earth, both cooling and heating the Earth. Water vapor and clouds are responsible for much of the world's albedo, reflectivity, but also most of the greenhouse effect for Earth's history. Compared to a completely dry atmosphere, the current concentration of water vapor has produced a much stronger greenhouse effect than the current concentration of carbon dioxide. But that is not a molecule-to-molecule comparison. Absorption of wavelengths shorter than about 4.2 microns, so to the left of my cursor, would have a net cooling effect, and higher water vapor concentration would increase cooling. This includes 100% absorbed blanket ranges and window ranges. It's complicated and requires complicated climate modeling beyond what we can do in this course. I assume the amount of water vapor in the atmosphere has been pretty constant over recent millennia, though I don't have data on this, while the amount of carbon dioxide in the atmosphere has increased by 50% over the last 200 years. Combustion of hydrocarbon fuels, oil, gasoline, diesel, jet fuel, natural gas, emits water vapor as well as carbon dioxide. Global warming increases evaporation, puts more water vapor into the atmosphere, and the atmosphere can hold more water. But I don't know whether or how much precipitation increases or whether low clouds increase or decrease. Climate scientists say that the net effect of additional water vapor is heating, amplifying global warming, but with considerable uncertainty. This is not something I can verify with calculations. To the extent that increased water vapor in the atmosphere increases temperature due to the greenhouse effect, water vapor has a positive feedback effect. Climate scientists say that water vapor is not the driver of present climate change. Carbon dioxide and methane are. But water vapor is a net amplifying feedback response to increased temperature. Water vapor is said to be the most important positive feedback in the climate system. The total amplification is a factor of 1.5 to 4.5, quite a bit of uncertainty. But I don't know how much is due to water vapor. But this is not runaway positive feedback, presumably because of clouds and precipitation. Increased temperature can also change the amount of cloud cover, which changes Earth's albedo, but whether this increases or decreases is complicated. Some articles don't list water vapor as a greenhouse gas. This is probably because it is mostly natural and only slightly human-caused. It has both a cooling and a heating effect. Or it may be because water vapor's effect is presently a feedback effect, not a forcing function effect, like carbon dioxide and methane. One reference said that a water molecule only remains in the atmosphere for an average of 10 days before it returns to the surface as morning dew or precipitation. But water vapor continually returns to the atmosphere via evaporation and transpiration of the water cycle. I don't know whether the 10-day figure refers only to isolated water molecules or also water droplets in clouds. Antarctica gets little precipitation but gets clouds. I don't know how clouds and their effects would change with increased temperature. One source says that higher temperature increases the amount of rain in rainy locations, but dry locations will get drier. As global warming melts polar ice and Arctic snow, Earth's albedo decreases, reduced reflection of sunlight to space, which heats the Earth. But water vapor in the atmosphere increases, both cooling and heating the Earth. Climate modeling must account for positive, amplifying, and negative, stabilizing feedback effects of increased temperature. It's complicated.